class. And what we are going to do, as we usually do, is that this time I'm going to ask you guys a few questions. So that way you will just quiz you on a few things. Let me close this guys here. Discard. That's right. I am going to share the screen. So do not worry. And I'm going to share away the share. Okay, share button is over here. Share address, and I'm going to share my document. Okay, folks, can you see my shared screen well? Uh, yes.
Yeah, we can.
Okay, good. Very good. Very good. All right. So, Toby, you will be my the person that I want to ask, and or maybe other people too. So, if you have any problems, just let me know. Okay, first question to Tobin. Maybe you unmute yourself. And in quantum mechanics, beside the probability density, how can we extract other physical quantities from the wave function? How do we do that?
Uh, by plugging in an operator and integrating.
Exactly. You got it. You got it. Let me see whether, yeah. So exactly, we use operators. Okay, next question. Next question is the following. What is expectation value of an operator? Aisha, what is expectation of an operator? What we call that? Well, why what is it, Aisha? So, what is expectation value of an operator?
Expectation value is the average value you get when you integrate.
Exactly. Good, good. Well, that's it. You see here. This is the essentially the operator itself. Now this is direct notation. If it's a not direct notation, we will do the integrals. That's essentially average value. And the point why sometimes we say expectation value instead of average value, sometimes it's actually not average value. Let me highlight this when that would be the case. Did you see I have two psi exactly the same? But in the future, you will see psi 1 and psi 2, they may be different, like this. They may be different. So, this is the operator, so I didn't write very well. So this is the operator. So then maybe these two are different. Then you cannot say this is the uh, average now because these two are different. So that's the main reason why we emphasize called expectation value. But if these two are the same, then we call it average value or expectation value. It doesn't matter too much. But when you have these two are different, then you cannot say this now. Okay, Cody, you're going to answer the third question. What is the Hermitian operator? How do we know an operator is a Hermitian operator, Cody?
The Hermitian operator is basically when you take the operator, but then you use the complex conjugation and the transpose it, and it just equals the regular operator.
Wow, wow, you nailed it. Okay, perfect. Thank you. You nailed it. Exactly. So this is exactly what you expect. Yeah, you see here, complex conjugation and that operator. So this you call it dagger itself. So, Tobin, go back to what is complex conjugate?
It's just taking the function and changing the sign on the imaginary
Perfect,
aspect.
perfect, perfect, perfect. Exactly. Okay. Aisha, what is transpose? So what is transpose? Uh,
Transpose is uh, flipping the the matrix that you have.
mhm. Okay, yeah, flipping, yeah. So yeah, just essentially just the upper diagonal elements becomes a lower left diagonal. Yes, just flip them over. Now for the regular operator like these, for instance, if somebody asks you, suppose I have this operator and I want to transpose this operator like this. Okay, suppose I have a differential operator, I want to transpose this. And uh, in our book, we proved it, but it's okay if you do not want to know how to prove it. This is actually equals the negative of this part. And you can prove it. It just need a few lines to prove them. In the end of the class, if I have extra time, I will show you this one here. So that's called a transpose. The operator, essentially, this transpose, did you see T here? In the beginning, if you have a partial, could you guys write this down? This is not in the notes. So if the partial x applied on the function, let's call it f, like this. And then it's going to take a derivative with respect to x, with respect from f, like this. However, if you have this operator like this, you have f, and you also have g. Could you guys write this down? In other words, if you have both g and an f in the front, this transpose is in fact going to apply to the g. In other words, the partial derivative is applied to the g, and you also must have the negative sign. So this one equals the negative f partial g over partial x. So this I will show you at the end of class on a piece of paper. That's make things a whole lot simpler. So that is transpose means. So just in this case, even though somehow the function behind this partial derivative, but it's not applying onto f, it's applying on the g. That's what transpose means. Good job. Okay, very good. So I'm going to erase this, and I have a few more questions. Suppose the A hat is an operator, f is a function. If they satisfy the following equation like this, what equation do we call? In other words, what kind of equation we call them, Cody? What we call this equation?
Is
So
that
we have
a eigenfunction?
exactly. This is called eigen equation, not eigenfunction. This equation is called eigen equation. Could you write this down? This is called eigen equation. Exactly. Now you revealed everything. What is lambda we called? Cody. What is lambda?
Um, is it the oh is that the Broad wavelength or am I
No.
floating?
This is just a number, not the wavelength. Sorry, I
Oh,
said
okay.
yeah.
Uh,
So we have what we call f, by the way,
F is the eigenfunction.
and what is the lambda in front of it?
Oh, is that the eigenvalue?
Exactly, exactly. Well, I should not use the lambda to trick you on this. So we call the f is eigenfunction. I'm not going to ask you. Okay, I'll go back to Tobin. What is a Hamiltonian?
It's the kinetic energy plus the potential energy.
Exactly, you got it. You see. So now you say that what it consists of now. Okay. So Aisha, if h psi equals e psi, what do we call the psi? Aisha, what we call
That's
psi?
the eigenfunction
Eigenfunction, also called
or the eigenvector,
eigenvector, also
the
called
eigenstate.
exactly the next line that I reveal the answer for you. What we called E.
Uh, the eigen, is that the eigenenergy?
Exactly. You know what's exactly? Yeah, you said it very well. So in this equation here, E, which we call eigenenergy, it's also called eigenvalue. In other words, it will inherit anything that we said before. Exact the same thing, whatever you can call this eigenfunction, and that's fine, but not other way around. In other words, we cannot call this one. But some textbooks still call f called eigenstate, lambda called eigenvalue, and but I kind of resisted this because you get confused because eigenstate which we want to be much more precise. Okay, so I think that's all the question have. All right. So one last question. Cody, what is eigen means? What does eigen mean? You remember, Cody?
It means itself.
Exactly. Good job. Good job. Okay, that's all that I have. Oh, one last thing. No. Kelvin, what is the Noether theorem? Noether theorem.
Yes, you know.
Yeah, we discussed last time. Look at the notes.
Um,
So this, I think, is the absolute last question.
oh, it's the way to like quote unquote derive the Schrodinger equation.
Yeah, we use that. And what's the key idea? Uh,
Momentum conservation
yeah.
or conservation laws.
Yes, yes, exactly. It just means that if you have in the physical system, if you have some quantities are invariant, and then it's going to correspond to the conservation law, whatever kind that is. Okay, that's very good. So, folks, that's it. I'm going to go back to the sheet that I'm going to start with, and this time I'm going to talk about the continuation, just review a little idea. We started with the momentum P operator. So that's a P operator. And this is classical world. And then another P, T plus delta T like this. And we said if after delta T, if there's no change, we call it momentum conservation, which we said before. And then in our case, we said we start with a row. This is not P row. If we have a situation, which means after some time, and this row oh, so there's no arrow on the top, forgive me, that a T. And they are exact same. Now, my spatial coordinate is hidden here. If I want to write, I need to put spatial coordinates, so I'll run out of space now. So spatial coordinates, it's not an issue, it's assumed. And so you see here, I use a delta, and here it's very important, is small. And when we write this book, in the beginning, my first draft was, why not tell the student you can have T1 and row T2 like this? So in other words, why I choose T and T plus delta T, not just T1, T2. And even worse, I could say, why not call it constant? You know, why not this? Why not derive in this way? I attempted. It turns out it's very bad theory, which we develop from this. The point is that you see, if I have a T1, T2, these two time instant are same, which means suppose you have a process like this. Let me sketch a diagram like this. Here's a T, and here's a point at T1, here point at T2. And I only know these 2 points have the same value. Can we derive it, use the same method? The answer is no, because you cannot expand around one of these variables. So this actually ends up nowhere. So in other words, the theory when you develop, it becomes much less powerful because you only connect with these 2 points. And what about if we set it to constant? Constant even worse. This means the wave function is going to be have a crazy features, and you are not going to be happy with that at all. Essentially, what I'm trying to say with it, if you do this, put them constant, you will get like this partial like this over t, and you will get something like this. It's a very boring expression like this, equals 0. So if you set to constant, and you end up with this one. So this is not a good theory, which means, and then this equal to each other. So it does not go anywhere. And so then once this failed, and I said, well, the only one that I need to do is just go like this. And this actually turns out what's the essence here. Now let me expand this further. We already wrote last time, we will have psi r t, and this equals psi r t t plus delta t. So this we already explained last time, and then we take square root of both sides, and this will take on a phase factor. So this will be something like this. And this time I'm going to move this term to the left-hand side and this term to right-hand side. So then I can expand this term. So I'm going to move this to this way. So I didn't do anything just except to move this to over here. to make things a little simpler to see them. So I move this term to the left-hand side. And here is a phase factor, e to the negative I alpha delta t. And then I have this term here, psi rt, like this. Again, I didn't do anything at all. Essentially, this phase factor, if you set alpha equals 0, then we'll end up with a situation like this, what I had before. It's very boring if alpha to 0. It's of course the solution, but there's no essential features developed from it. So it's essentially very boring results that I will get. So I won't do anything. Now, you may wonder why I put a delta t there. Well, if I do not put a delta t, I still have the equation because I absorb into alpha. And this one has a beauty. You see, if my delta t equals 0, and then it's still valid. So this will go back to everything that we assumed before. So this is the feature that I want. I want add delta t there. So this is the feature 1. I'm going to call it feature 1. So the main reason why I have this phase factor is because it allows me to go back to the initial condition. So I can go back to the initial condition easily. So I just go back to the initial condition. So if I say the delta equals 0, delta t equals 0, it allowed me to do this. And this is the feature number 1. Feature number 2, did you see here I have alpha here? There's nothing special about this alpha. I'm going to interpret this alpha in this way. So I have alpha. Now, this alpha can be just a regular number, not an operator. So I will make this guys to become an operator. I put a hat on the top. And you may ask why I want to do like this. Well, this is where the new physics built into it. Let me show you why new physics built into it. Suppose I have a function, and I want alpha multiplied by function, and this still a function, let's call it g. So I have a known alpha, a known function, and multiplied by this also a g. In the meantime, if I have an operator, applying a function, and this still a function. So in other words, going from alpha to alpha hat, I didn't lose anything. I didn't lose anything because I still can use the scalar function. So this scalar function. So from here to there, I do not lose anything, but I gain an operator. And I gain an operator. Going from here to there, and I gain an operator. I didn't lose anything. I gain an operator, and that's where the physics built into it. That's where physics are built into it. So this is a step. It's very difficult to know why we do this. So essentially, you can go back to very boring case, put alpha equals 0, but that's not what we want. We want to move build in additional things into that. So now, once we agree on this, then we can expand this a little further. So I'm going to expand this function here in our Taylor series. So I expand this into Taylor series, it becomes to look like this. The first term is alpha t, the RT, so that's initial term. And then I will expand up to maybe second order of t, like this. And this will be delta t, like that. So I expand this term. And then, of course, you have higher order terms here coming into play. Now, you realize why this is small. Because if this is small, I can drop out these terms. Why I cannot use this? Because I cannot expand these two. These 2 points are really far apart. So this expansion is dead. You cannot expand this because this T1 as a T2, you can expand it into T1, T2. So that's why I deadlocked over here and I have to go back. Okay, forget about this. So I have to go back like this. Any questions so far, Tobin? Is that good?
I was wondering where in the equation at like the top of your camera right now,
Which one?
down a little more. That one.
Mm.
Where did I was confused last class. Where does the e to the negative I alpha delta t come from?
I see what you're talking about. So you were wondering how in the world you jump out this term into the
Yeah.
first place. Okay, good point. Let me explain it. Let me explain it. So I am going to use very simple example. Suppose psi r t plus delta t equals negative psi r t like this. Suppose now you see this equation satisfy this equation, right?
Yeah.
I simply put if I take absolute value, square this guy, and it will be go back to this equation. This equation can go back there. Let me call it
Yeah.
equation number one. This equation number two. So in other words, I can go from one all the way to no problem, right?
Yeah.
So I put a negative sign. Now, this negative sign, I can write in the exponent e to the I. You see that e to the uh, negative I pi over 2, like this. Does it make sense to you? Negative pi over 2. And this will be side like this. In case if you think you get lost, let me explain this one to you. So this is just cosine alpha plus I sine alpha. And this will be negative sine. So sine alpha, just 90 degrees will be pi. So this phase factor, in other words, whenever I have this phase factor, I always can in other words, whenever I take square root out, I always can put the phase factor in the front. Here is a reason. Let me show you why this is the case. Let me call this one Toby. Let me call it gamma. Let me call this entire term is called a gamma. Toby, let's do this. I think that is probably much simpler than this one here. This is just show you a special example. I call it gamma. Tobin, you see, I didn't do anything. I just put the gamma in the front. I didn't do anything. Fine, right? I didn't do anything. It's just
Yeah.
so now this is assumed. This is assumption. This assumption. In other words, we don't know. Now we are going to do this job, which is take complex conjugation. Complex conjugation. Complex conjugation. So then I multiply both sides, both of them multiply by each other. So then what I will multiply by each other, which means it's going to become psi star t plus delta t. Psi, there's no star now, t. And this will be gamma star. And then, sorry, a round of space, psi t star, psi t. So this is the equation which I have. Now, left-hand side is just my top equation here. So these two, let me rewrite this. This is just psi t plus delta t. Are you good from here to this? So the
Yeah.
left-hand side is this, right? Are you good?
Yeah.
So then this will be gamma star, and this will be psi r. So this is t. They're like this. So then you can see I have a term gamma star, and this has to equals 1. This has to equals 1 because my assumption in the beginning there is a 1. So therefore, my gamma star must be equal to 1. So this means that I can choose anything that I wanted. I can choose anything that I wanted for gamma equals 1. The most generic one is this format. Most generic one is this format. In other words, most generic one is just for this format. If you choose a real, then this gamma will be equals plus minus 1, right? If you choose a real, plus minus 1. But for the generic ones, I can choose any. So this is the generic solution. The generic solution will be e to the I alpha delta t, like this. So this is the generic solution for this particular number. It's a little bit convoluted. That's why. So this Does it make sense to you now?
Yeah, so is it like some sort of constant to correct the value
Exactly,
or
exactly, 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 exactly.
okay.
It's just a constant in the front. I just, in other words, I can make these things very boring and make them too real. Then there's nothing gained. There's nothing gained from this. So when I started deriving this equation, I can make it real boring, which means that these two equal to each other, and that didn't tell me anything. But quantum mechanics is just built in the complex number. Folks, could you guys write this down? Complex number theory. In other words, the quantum mechanics, it built in the complex number theory. It's always complex. If we just quantum mechanics, if without complex number, quantum mechanics stopped. And so, so that's why we, and in some sense, like quantum mechanics because we want to have these complex number. And you're gonna see this I all the time, this imaginary symbol all the time. Okay, I hope Tobin, I answer your question. It's
Yeah, that
not
helps a
very
lot.
convincing. How you can prove? You have to choose this. No, I have no way to prove it. As I said, this is not deriving the Schrodinger equation. This is essentially I know the answer, then I can find how do I get that answer out. This is just fitting. I hope you are satisfied enough. Okay, sounds good. All right. Any other questions? Any other questions? No, Cody, Aisha, if you have a question, you can put it in the chat box. I will be able to read the chat box. Sounds good? Okay, very good. All right, I'm not going to force you to write type yes or no. But if you have questions, just like Toby, please speak up. Sounds good? Okay. All right, now, so this is what I have. Just remind you, we are expanding this term here. So this expand. I'm going to copy this to the next sheet. Otherwise, I refer back and forth. I don't like it. So I will copy it. You don't need to copy it. I just want to show you entire sheet like this. So this is the one that I expanded partial t delta t. And I have extra terms. And my the right hand side, I'm going to use this copy this down as well. So e to the I alpha delta t psi, and this is the t. And I'm going to expand this term, not the psi. I expand this one. So this just gives me 1 minus I alpha delta t. And then, of course, you have a whole bunch of other terms, psi t, like this. Okay. So this is what I have. So these two equations, sorry, my handwriting a little crazier. So this is my left-hand side, this is right-hand side. And these two has to equal to each other. So I'm going to write both sides. Psi t plus partial t delta t. And this is going to equals 1 minus I alpha delta t plus additional terms. Like this. Now the first term cancels out. You see 1 times psi, they cancels out. So the second term is our equation. Second term, the delta t cancels out. So I will get I alpha psi t like this. And this is, everybody, this is, oh, sorry, I forget. Folks, I made a mistake. I should have hat on the front, in the front. I didn't say hat. Okay. So this is our final equation. And I'm so proud to tell you, this is the one I really enjoyed it. And let me move this I to the left-hand side. So multiply by I both sides. Okay, like this. So this will be I psi t like this. So this negative I, positive I is gone like this. T like that. Okay. And now I'm going to multiply by h bar both sides, h bar both sides. Okay. So this is h bar both sides in this way. And this particular part is Hamiltonian. And this particular part is the Hamiltonian. In other words, what I did was I let alpha to choose a special property for myself. So what I did was I choose alpha
Can
to
you slide
be,
the paper down just a little bit?
oh, forgive me,
Thank you.
to be, is that good now? Okay, to be my Hamiltonian. So in other words, I started from the beginning all the way to that. I did not reveal my secret card until now. In other words, I did not use the, because Northern theorem says that you need to tell me which one is the actual physical quantity. I hold off my card. I just closed my eye, didn't do anything until now. I say, okay, this is my Hamiltonian. Then I have energy conservation. So now I have energy conservation. Did you remember before we have a momentum? Before we have momentum, with momentum conservation, I revealed this to you in the beginning. Here I did not reveal it until now. I say, aha, everybody, I am is the children house or uh for your army, then I'm actually the Hamiltonian. Then you reveal self. Okay, so this equation is should time dependent Schrodinger equation. This is time dependent Schrodinger equation. I did not see any other place actual people use this way to derive it. I look at Fermi's derivation. Fermi's derivation is a little more hand waving too. So then I decided I need to find a good way. And this I found is very useful for our purpose. So that is what we use. Now, any question on this so far? Any question? Just wait a second. Any questions? I just do not want to rush through it. Aisha, any questions? Cody, any questions? Can you guys give me a little response? No or no question? Just type in the chat box. So hope you are satisfied. Can you
Can you
find
slide the paper down just a little bit more? I missed part.
which part?
Just scroll down a little bit more. There.
I,
I didn't write down the expansion part, and I was
oh,
trying to.
sorry. Okay, yeah, yeah. Let me. Okay, sure. Okay, very good. So this is what I wrote like this. Okay, and uh, this is the Schrodinger equation, which we'll deal with entire semester. Essentially, this equation is our sort of the bread and butter. We will utilize this a lot. But before we do anything, let's play with this equation first. Let's look at the units. Tobin, you are good now. Did you write this down, everything?
Yep. Thank
Okay,
you.
very good. So I'm going to move upward now. So let's look at the units. First, let me look at the units. So I want to look at the units. So here is my units, and I want to show you what actually this units could be useful. H bar has joule second. H bar has joule second. The time has second. So you see left-hand side units will be joule. Now the right-hand side, I have H. H has joule. You see the both joule, joule. So the units are consistent. So that's the units. Second, now our psi has a unit. We mentioned this to you last time is square root cubic meter, like or square root of 1 meter, like this. We mentioned this before. Let's play with this a little bit. Let's put the complex conjugate. Let's put the complex conjugate onto this Schrodinger equation. Complex conjugate, which means I need to put the imaginary becomes the negative. So you will see me, I'm going to write this down. Negative I H bar, put a star in front, partial t like this. And I will put star like that beside t like this. And this is complex conjugate. Complex conjugate in this way. So that's complex conjugate. Now, I cannot show you immediately what will look like the H star, the H bar, except if I will write this H hat out. So there I have the kinetic energy operator plus potential energy operator. So then I can show you what this is. So I'm going to write this down now. H star and T star plus V star like this. So that will be conjugation comes out. And I want to be one more step further. I want to show you what the kinetic energy operator. Our kinetic energy operator looks like this. H bar square 2m. And this part is a del squared. It's just a Laplacian squared like this. It's just a Laplacian operator. And so therefore, if you put a star like this, so this will be equal to t. Because this everything is here is a real. Now, one thing, this guy is trickier. In other words, normally, so I'm going to write this down for the potential. So here's a potential. Potential normally is a little bit strange. For a closed system, I will explain what this closed system is. V star equals V. For an open system, V star not equals V. In most of quantum mechanics books, they all deal with a closed system. What do you mean by closed system? It means this. So this is the system is closed system. It has no interaction between environments. So here's a system. Here's environment. So there is no interaction between these two. So this is a system called closed system. Open system means there is interaction. So therefore, this potential will not be the real. It's complex number. And this open system, where you can see the open system, is this guy. Here is my battery. Here is my resistor. And this is open system. This is open system. In our most of our discussion, we do not have a battery. We just have a resistor around it, like this. And so therefore, it's always closed system. So that's why this potential is a very tricky problem, which we do not deal with them. And this is in the chapter 9. Chapter 9, we deal with the open system. Before chapter 9, everything is closed system. So my V star, V always equal to each other. If we use a closed system, and that will be exactly the same. So we can like this. So just remember, this is the closed system. It's not an open system. It's closed system. So these two psi are exactly the same. So there's no difference whatsoever. Any question on this? I will pause here for a second. It's quite condensed in this case. I don't want to overwhelm you on this. Any questions? Okay, it doesn't seem, Toby, do you have any questions on this? Okay. And for the moment, I only show you a complex conjugation. And so this is the equation which we have. And now, if I want to do the transpose one step further, just save my space, I can do plus another transpose. Now, when I do the transpose, and the real function doesn't do anything. So this is the transpose. Now remember, this is not an operator. So therefore, real function does not do anything. It's just still keep as it is. But the operator does. This operator essentially will apply to the front. So that's why what I do, I will write it like this way. put psi into the front, apply into the front, and then we will write this one like transpose. So we use a dagger now. This is a dagger in this way. So this is called a transpose. So this transpose move this wave function to the front. And this looks very, very uneasy. Why it's uneasy? Because students get confused with, okay, you transpose I, now I see what you're doing. You basically, if you have operators, you swap these two. If you do not have operator, you don't swap. Yeah, the answer is good. Is that correct? Then you say, what about this partial t? Do you transpose this one? No, we don't call it transpose. That's called a time reversal. So this is a non-trivial. In other words, we introduced called a time reversal. I do this transpose, this for the space. Transpose for the spatial part. But if I transpose for the time, we call it time reversal. I learned this hard way because, well, you told the student you transpose this whole things, but now when you transpose the time, we call it time reversal. So, and student learn the harder way in the sense that transpose this spatially, we just redo the transpose, but the time we call it time reversal. So that's kind of a trickier in this case. So we're not reverse the time, so that's why we keep this operator as it is. By the way, I reveal all the secrets that all these books try to hide from students. They will transpose for the spatial operator. Yes, you just flip them over. The transpose for the time is actually time reversal. You just flip this time and go the other way around. Now, Dirac doesn't like it. What Dirac invents is the. Do you have any question on this sheet before I move it? Any questions? You can take screenshot if you wish. You can take screenshot, so that will be allowed you to have this sheet in front of you. Anyway, so I move to the next sheet now. So in other words, I didn't do anything, but Dirac invented his notation to make things much simpler to see it. Let's look at the Schrodinger equation. For the Dirac-Schrodinger equation representation, he's going to represent and look like this. So this is the Dirac representation. If you do the transpose, then it's very easy to see them. And this becomes to look like that. So he put it this way. So you see the brackets go this direction. And then this brackets go this direction. And this complex conjugation transpose already have like this, dagger like this. So put it this way. Now because the harmonious Hermitian, this also equals H star like this. So you see, Dirac notation, it does reveals this guy actually flipped to the front. But for the Schrodinger notation, you see, this is the strange in the sense that you see here like this. This is the Schrodinger. Oh, let me put them together. I want to make sure. You see, in this is the Schrodinger representation. If you transpose it, you do not see this guy to the left. But for the Dirac notation, you can see this actually to the left. So that's why Dirac's notation is a really, really powerful way to representing this. Okay, so you see this will go this way now. So you can clearly see the difference. I hope you soon or later you will like this better because I found this is much simpler than this. You put a star there, but this is, remember, we did not reverse the time. And so that's why it's kind of ugly in this case. Any question from any one of you? Because I'm going to move on to the next section. I will not discuss the current operator until the next time. Any questions? Could you type no question, please, so I know you have no question or respond in some things. Tobin, do you have any question on this? Okay. Yeah. Question.
I guess what, hold on, I'm trying to figure out how to word it. So Dirac notation is just telling you like where the partials are with respect to psi.
Yes.
Is that what it's doing?
Yes,
Okay.
yes. So at least you see here, you know this guy is to the left. So you can see the difference. But this guy you cannot see the difference because he's just put a star on the front. if you compare it with the original Schrodinger equation, which is the Schrodinger equation here, you essentially put a star like that. The transpose portion is missing because you see here, this is a not transpose. This is the transpose. You see the transpose, they're exactly the same, right? Because this is a function. You cannot rotate the function this way. If a matrix, you can rotate. You see, these are exactly the same, even though it also both transpose it. You did not see it. But for the Dirac notation, you do see the difference. You see it from here to there. So you do see the difference in this case.
Okay.
Okay. The current operator I would ask you guys to read after class. And I will use the last few minutes to move on to the time-independent Schrodinger equation. And this part is actually the most important part. Time-independent Schrodinger equation. The most important part is really time-independent Schrodinger equation. Time-dependent Schrodinger equation, it just gave you a framework how you work out. Now I'm going to talk about time-independent Schrodinger equation. This time I would use a very detailed notation. First things that I want to explain it, time-independent Schrodinger equation. Schrodinger equation, I just simply use SE, is an eigen equation. So time-independent Schrodinger equation is an eigen equation. So I want to show you why this is equation, and it's based on two assumptions. Based on two assumptions. So this is a really based on two assumptions. And we will explain why you can make this assumption shortly. So based on two assumptions. The first assumption, assuming H is time independent. Assuming H is time independent, I want to put a notation subscript, put O there. Just remind you, this HO may not be the same as H before. And I'll explain when you can actually deal with this original H in a second. So essentially, this H itself is time independent. It must be. Second, superposition principle. And you and I must agree on this superposition principle. If we disagree on superposition principle, then this whole thing will break down. I just want to borrow just a few minutes. Just let me explain why this time the dependent Schrodinger equation when the becomes the time independent Schrodinger equation. I just only need maybe 5 minutes to explain this to you. It's relatively straightforward. This time, just save my notation. I'm going to denote partial psi. Denote, I put the dot on the front, on the top, so forgive me, on the top. I would denote this following way. So therefore, I can write the Schrodinger equation a little bit simpler. So I put the dot like this, H. And I put O here, psi like this. Okay. And this is a time-dependent Schrodinger equation. Since I assume H naught is going to be time independent, so I would be able to calculate two dots. Because H is not a time dependent. So it doesn't matter whether I take time derivative or not, still remains the same. Put a dot like this. Otherwise, I will have a time dependent on the top. So that's that. Now I'm going to make a trick. Did you see the h psi dot equal this amount. So I can both sides divide by IH bar psi. So in other words, I'm going to replace this guy, use this equation. So I would have like this. IH bar psi, like this. H bar multiply each other, it becomes H bar squared. Divide by psi, like this. So this is the square, like this. So because they multiply each other, it becomes squared. Now, in principle, I can do this forever. In other words, what I want is exactly the same thing. Let me divide by this term divide both sides. So there will be two dots. It's going to be parentheses h0 IH bar square psi. Now I can do something. This could be to any infinite order. So suppose I have take derivatives to nth order. So this to the nth order derivative. Then I would have h bar hat, forgive me, hat, IH bar like this. Nth order psi. And this reveals something very special. So this means that this tells us we have a way to separate the spatial and temporal means time, degrees of freedom in our wave function. Because whenever I take a time derivative, it's this guy just have one order high. And this is essence of the time-independent Schrodinger equation. And next class, you're going to see me, I'm going to separate spatial time-dependent part. What that actually will see, you will see me write down. Originally, I have the equation like this. These two couple to each other. We don't like it. We will write in the following way. And this is just separation of variable. This ENM utilized. You remember ENM case, we will separate x coordinates, y coordinates completely, and here's exactly the same method used. In other words, you will see me instead of use a psi, we use a phi now, and here we have a t, and here's a phi. And this two part is going to multiply each other, and the equation end up with this phi is going to be called time-independent Schrodinger equation, and that will be for the Wednesday's class. Okay. All right, that's it, folks. Any question before I close this? Any questions? What is this? Sounds
What do you
good?
mean by the temporal degrees?
This is the time.
Ah, okay.
Time degrees freedom. Let me use the time. Maybe use the space and time. Space time degrees freedom. So space degrees term freedom and spatially and time they will be separate. The one that's separate out from this time degrees freedom, and it's the spatial portion of that. So entire semester is about this guy, not this anymore. And we will show you a whole lot more detail and on Wednesday. So this is the first class. Just show you on Wednesday. You're going to see me start with this equation to derive a whole bunch of the other ones. Any other questions? Aisha, any questions? Cody, any questions from me? No questions so far. All right. What I will do for all of you is that I will take a screenshot for these 3 sheets. So that way you have a copy of my lecture notes. So essentially, I will try to take a screenshot and send this to. I will put in the chapter 2 notes, and there, and I also will upload this video to the Canvas as well. All right. If there's no more questions, so that's it, folks. And I'm gonna end this now. I'm gonna stop recording. Yes,
Dr. Zhang,
question.
do we have homework due this Friday, by the way?
Homework will be assigned today, essentially. Today will be
Okay.
assigned homework, yeah. And then I will send out announcement so that way at least you have a few days, yeah. Otherwise, I don't
Awesome.
want to
Thank you.
rush through it. And so this will be mainly on the last chapter number 1, and then maybe a small problems for this chapter, and there's no
Okay.
more. Yeah, sounds good. All right. So I haven't graded homework yet because I have on Wednesday, on Fridays was busy and today's a day off, so we won't do it be anything. Okay, any other question from any students? Any student? I shall make sure you get account from HPC. Cody already has account, so I shall make sure. Toby, could you talk to each other? You guys talk to each other, so make sure Aisha could have account because I will show some programs on HPC very quickly. Sounds good, Aisha? Okay. You
Sounds good.
okay. You guys have a communication way to do that, right? You maybe phone number,
Yeah, we
whatever.
do.
Okay, good, good. All right. So that's it. I'm gonna stop recording and see you guys Wednesday, and that's it. Let me stop it. Where is the stop recording?